Here's a second example of hypothesis testing for means, what we call a t-test. And in this case, we're going to see how we can use the technology. In an example, we're not starting with the raw data like we did in the first one. So in this case, we're going to start with a summary of the data that's collected rather than the raw data itself. In this problem, we're going to start with some baseline information about what a normal blood pressure would be within the population of American women ages 18 to 44. So we're going to start with the generally accepted population mean of 75 millimeters. It's, where is it, right here, 75 millimeters, as the generally accepted mean blood pressure for American women in this age group. What we're trying to find out is if regularly exercising actually can lower your blood pressure. And so to do that, we're going to randomly sample 10 women who exercise and take their blood pressure, take the average of those 10 readings, and then see if that provides enough information to make a conclusion that within the population of exercising women, the blood pressure is lower. So we start off like before, carefully stating the population parameter that we're testing here. And in this case, we're testing the average blood pressure reading. So this is the diastolic blood pressure reading. There's two numbers. And that's in blood pressure measurement is measured in millimeters of mercury, of all things. Blood pressure among all, I'm not going to try to write American ages 18 to 44 or whatever. I'm just going to write all exercising women, and we'll just remember that that's within the category of American women ages 18 to 44. But the key thing is that we're talking about the blood pressure among the population of women who exercise. If there is no effect of the exercise, then that would mean that the blood pressure among the women who exercise is the same as the generally accepted average in the overall population. So mu equals 75 would be a way of saying that exercising does not actually lower your blood pressure. And so we could say, just in words, there's no effect of exercising on your blood pressure is our H0. I'm going to point it out that way because for some of the next, in the next unit, where we talk about testing for association, in those cases, the null hypothesis is always that there's no association, no effect of whatever it is we're testing. So this is consistent across all of the different kinds of hypothesis tests that we'll do. In this case, the alternative hypothesis, this is actually a two-tailed test that's being described, and we can tell that because, and I've tried to even make it bold here, the explicit thing that we're interested in is the blood pressure among exercising women less? And so this would be a way of saying exactly what is highlighted above. So when we do want to have that alternative hypothesis be a less than or greater than sign, it'll explicitly say that in the problem somewhere. If a problem does not say explicitly whether they're talking about testing a claim about less than or greater than, then we always will just use not equal to as our sort of default decision about HA. So I'll put in parentheses here, just a reminder, this means we're going to be doing a one-tailed test. When I draw my picture below, I'm going to shade in one direction, and I know that I'm going to shade in the direction of the of this symbol, so I'll be shading to the left. All right, so now we're ready to draw our picture. We want to draw the picture of what X-bar distribution would be, how the X-bars would be distributed under the assumption that H0 is true. If H0 is true, H0 literally says the mean is 75. So if that's true, then the middle of this distribution will be 75. So the center of that distribution always comes from the statement of H0. Now, to label it, I also need to know what the tick marks are, how far apart the tick marks are. And just like before with proportions, that's called standard error. So I need standard error equals, the exact formula is this, sigma over the square root of n. We're generally not going to have sigma in front of us. So we will approximate by using the sample standard deviation, which in this case is given to be 16. And we're dividing by the square root of the sample size. The sample size is 10. So I'm looking up here and grabbing these things. There's S, there's N, and so that was what goes into that calculation. So oh, I didn't write 10 down. I wrote N. Sorry, 10. And so to a couple of decimal places, that's 5.06. So 5.0596, so rounded off, that'll be 5.060 even, 3 decimal places. And so that's about 5. And I always try to round that off to a nice number for my labeling, just because I don't want to have to make my labeling too arduous here. So if I use 5 for the size of the tick marks, then I'll just be going up and down by 5, like that. All right, so that's what the world would look like for how our X bars are distributed. If the null hypothesis is true. Now I take data and I compare my actual data collected to that hypothetical picture. So in the problem statement, it tells me the X bar, it tells me the mean of the sample that I collected. It says that that is 71 right there. So that 71 is the mean of among the 10 women who exercised. In other words, the mean among the sample that we gathered. The t-score, the test statistic, is always observation minus the mean. The mean is the center of the picture that I drew, divided by the standard deviation of the picture that I drew. So I'll use 5.06 to be more precise. And that is about, what is that? Negative 0.79. So my t-score, negative 0.79. And that should be borne out if I were to draw my 71 on this picture. It would be about here. And you can see that's to the left of the center, but not quite to the first tick mark. And that's what negative 0.79 would be. You're 79% towards the first tick mark, but you're not quite there yet. The part that, that we really have no way of doing without some kind of technology is the part where we're shading the stuff. So because the HA is a less than statement, that means we're going to shade to the left. So my shading in this picture would be to the left of 71. If I transfer that picture down here on the t-distribution, then this t-value, negative 0.79, would fall in the same position relative to this curve that the 71 was on this one, and my shading would still be to the left. So the p-value is equal to the area of this shaded bit. And remember that total area under the curve is 1, so it really is just the p-value is just the proportion of the curve that's shaded. The applet that I've been using, it's the same one that we used for the other example, and it's on this handout again, returns the value for my p-value 0.2248. So a little more than 22%, and that looks about right. The picture looks to be about 22% shaded. Good enough. Oh, I wrote that down too soon. Anyway, that's the number that goes into this blank. Whether, almost regardless of what we're testing at here, it does tell us that we're testing. It does tell us that we're testing at the 5% level here. So we know that that's our definition of what small means. But in this case, 22% is not really small by anybody's measurement. So the p-value is not small. And remember, the 0.05 significance level is what you're comparing it to. So 22% is not small compared to 5%. And so we don't reject the null hypothesis. Remember that when we're choosing these conclusions, we're either taking both the first ones or both the second ones. There's no combination of the two. If our p-value is not small, then we do not reject the null hypothesis. And so we do not have sufficient evidence and then we just state HA as best we can. So HA was the statement that the exercising women's blood pressure is less than 75. So we're saying we don't have sufficient evidence that we could just say it very broadly, exercising reduces blood pressure. Right, so exercise reducing blood pressure is basically the HA statement. Saying mu less than 75 would be a way of saying that exercising women's blood pressure is less than 75. So I can say it in words without having to talk about mu or hypothesis or whatever. On this handout or this printout thing, I keep saying handout even though I'm not there to hand it to you. On this document, there's a page that has a screenshot of the way you could enter all the information from this problem into the web app. That's the URLs at the top there. And you can see that not only does it do the calculations for us, but it also draws the same picture. And so we can feel pretty good about ourselves if the picture that it draws there is the same as the picture that we drew as we worked our way through the logic of the whole situation. And then finally, there's a third page on this that is a problem for you to try, following exactly those same steps. This document also is posted in D2L under the daily work 6 assignment. So it's the same document posted twice, so you can find it easily. Notice in this one, we're working with data again. So we're not working with summary, we're working with the actual raw data. And that's like example 1, not the one we just did, but the one that was on the previous document. So working with the raw data was more like that. This one does say we want to find out whether the size of the cans is different from 16 ounces. We don't really concern whether it's high or low. We just want to know if we're off from 16 inches. And so for this one, our alternative hypothesis is going to be not equal to. And that means we should be doing a two-tailed test, which means when you get down to this point, you should have shading in both directions. So you'll be shading the symmetric stuff out in each direction. So that should be what happens for that. The rest of it follows exactly the same way. There's nothing really different about the way we set it up and the way we read off the results for this, but it is a little bit of a combination of example 1 and example 2 in terms of using the technology and getting the setup right.